Hi, and welcome to this section of the Advanced Calculus 2 Tutor. And in this section, we're going to pick up where we left off in the last section where we talked about hyperbolic functions and their derivatives. And here we're going to talk about the inverse hyperbolic functions and their derivatives. So we're following a pattern. The beginning of the course, the beginning of the entire course, talked about the inverse trig functions and the derivatives of those. Now, the last section we talked about the hyperbolics, and now we're going to talk about the inverse of those hyperbolics and the derivatives associated with those. So it's just another thing to file in your brain, remember on your test, so that you know how to take those derivatives, and so you know about the inverse hyperbolics. So there's no mystery here. We've already talked earlier in the class about inverse functions in terms of the inverse trigonometric functions. Here it's no different. If you have the hyperbolic function, hyperbolic sine of x, then its inverse will simply be hyperbolic inverse of x. Okay, so these are opposites of one another. And if you had the cosine hyperbolic of x, its inverse would be the cosine hyperbolic inverse of x. That's what this negative 1 raised to the power here. That's not an exponent. That's not raised to an exponent. That's just the symbology of the notation that means inverse function. So what does that mean? Okay, what does this inverse thing mean? Just a little review, because we covered this quite a bit in the first section. We talked about the inverse trig functions. Okay, if you had hyperbolic sine, okay, of some number y, and that returns some number x, you plug some number y into here, whatever it is, and you get a number x back, then what it means is that the inverse hyperbolic of x is going to equal y. So you see they're kind of opposites of one another. If I have a number and I put it in the hyperbolic function and I get a number back, then if I take this number that I got back, put it into the inverse, I will get the other number back. So it's exactly the same as the inverse functions we talked about with the trig functions. Exactly the same. If you go back to that, we talked about the fact that if you take a number and you put it into the sine function, you get a number back, and if you use that number and go into the inverse sine function, you'll get your original angle back. So this is really the same thing. It's just dealing with hyperbolics instead. So that's just sort of a little bit of motivation here at the beginning to show you that these inverses are really exact analogs of what we talked about before when we talked about inverse trig functions. Now what we're going to do is just go ahead and, I'm not going to prove them or derive them, I'm just going to write them down, the derivatives of these inverse hyperbolics, and then we're going to use them to solve some problems. Okay, the derivative of the inverse hyperbolic sine, okay, is equal to 1 over square root 1 plus x squared. Okay, the derivative of inverse cosine hyperbolic is 1 over square root x squared minus 1. Okay, so you see there's already some similarity here, but they're not quite the same, obviously. Derivative with respect to x of inverse hyperbolic tangent of x is equal to 1 over 1 minus x squared. And you'll see a little bit of similarity here. The derivative with respect to x of the inverse hyperbolic cotangent of x is going to be equal to 1 over 1 minus x squared. And what you notice right away is that the derivative of the inverse hyperbolic tangent is exactly the same thing as the derivative of the inverse hyperbolic cotangent, which is just 1 over 1 minus x squared. Okay, so moving on, the derivative with respect to x of hyperbolic cosecant inverse, okay, the inverse of the hyperbolic cosecant is negative 1 over x times the square root of 1 minus x squared. And finally, the derivative of the inverse hyperbolic cosecant is equal to 1 over absolute value of x times square root of x squared plus 1. Okay, so here they are in all their glory. I make no effort to prove them to you. That's, in my opinion, what the book is for. I'm just trying to help you solve problems and give you practice with it. But in the biggest sense, I mean, really, there isn't that much to understand about it from a practical point of view. I mean, you have these functions. They're the inverses of the hyperbolics that we've already talked about, and some very brilliant people have derived their their derivatives, the derivatives of these inverse hyperbolic functions, and they're given here. And they're similar. These are differ by a negative sign here. These are exactly the same, and these are very similar as well. Okay, so those are they. So the next thing we're going to do is just work some problems applying that. Okay, and we're going to work those right here. So let's say, okay, you have a problem and it says f of x is equal to hyperbolic cosine inverse of x squared. Okay, and they said, well, go ahead and take the derivative of that and go ahead and practice that. So the first thing you know is that you have an inverse hyperbolic here. You got a different argument than just x, but you have an inverse hyperbolic. So you want to go over here and look and find, and you see right here you have the derivative of this inverse hyperbolic right here. So you need to go ahead and use that, but you're going to need to use the chain rule. So df dx is going to be equal to 1 over the square root of, now it's x squared over here, but this is if the argument were x, then the derivative would have an x squared. But the argument is x squared, so you need to go ahead and put x squared here and square that, okay? Minus 1. Basically, you're taking the argument you have and you're plugging it into that. That's the first step. And then you multiply by the derivative of the inside to make the chain rule complete. So the derivative of x squared is 2x. So you see, all we did was we took what we knew the derivative was and we plugged in the argument we had, x squared squared. And we go from there. So then df dx is just simply going to be 2x on top over the square root of x to the 4th power minus 1, because 2 times 2 is 4 when you have an exponent raised to an exponent. 2x over square root of x to the 4th minus 1. That would be the answer. That's the derivative. So you're using the same tools and things that you know from your chain rule, and you're just applying it to these particular functions here. F of x is inverse hyperbolic tangent of x over a. Okay, a is just a number, it's a constant. Okay, so how would you take the derivative of that? Same sort of thing. You know you have inverse hyperbolic tangent, so you come over here and you find out that this is the derivative of that, but the argument is different. So the first thing you do is you use what you know and you plug in the argument that you had. 1 minus x over a squared, because it was x squared. I just plugged in the argument I had squared, and then in order to make it complete with the chain rule, I have to multiply by the derivative of the inside, which just is 1 over a, because this is like 1 over a is multiplied times x. It's like 1 over a times x, you see right there. And this is just a number, it's a constant. So the derivative of this thing is just equal to what's out front. It's the same thing as saying the derivative of 2x is equal to 2. It's just that in this case it's 1 over a. So in order to finish the problem off, you say df dx is just simply going to equal, let's go ahead and multiply this a through, because you have a fraction multiplied by a fraction, so you can just multiply this a across. It's going to be 1 over a minus, and then you're going to have a times x squared over a squared, just squaring both terms in here. I just left the a alone, and then this is going to equal 1 over a minus x squared over a. Okay, all I did here was multiply this a, cancels with one of these a's, that's all I did there. And this, just to make the whole thing tidy, just to make it a little bit prettier, you can multiply this whole thing by 1. You can multiply by a over a. So you can do it again, and that's just going to make it look prettier. So df dx, because here all we did was multiply by a over a, which is 1, so we haven't changed anything. So on the top we're going to have a, and on the bottom you'd have a squared minus x squared, and that would be the answer. Now, even up here you had the answer. You're just doing simplification. I mean, this is just making it look pretty so you don't have this ugly fraction on the bottom here. A over a squared minus x squared. You took the hyperbolic tangent inverse, you took the derivative and you plugged in the argument you had, then you had to multiply by the derivative of the inside, and then you just multiplied the a through and multiplied the numerators. You got this, and then because of this, the nature of this fraction after we did the cancellation, we said, well, let's go ahead and multiply by a over a, which is just 1, to make the bottom look a little bit prettier. Some teachers care about that and some don't. So I like to show you that stuff just so that you can get some practice. What if you had f of x is equal to the inverse hyperbolic cotangent of square root of x squared plus 1. So here you have the hyperbolic cotangent inverse of a pretty ugly looking radical. Again, it's the same thing. It's the chain rule. It's just that this one's going to get a little bit uglier. So you come back over here and you find that, look, I know what the derivative of the inverse hyperbolic cotangent is. It's 1 over 1 minus x squared. So I need to plug this argument in here as a first step. So it's going to be 1 over 1 minus, it should be 1 minus x squared, but in this case, it's square root of x squared plus 1 squared, because the derivative is 1 over 1 minus x squared, but I have to use the argument I was given first, and then in order to make it legal I have to multiply by the derivative of the inside. So never forget how to take derivatives here. You have square root of x squared plus 1, which by the way, square root of x squared plus 1 is like x squared plus 1 to the 1/2 power. That's what the square root is. So in order to take the derivative of this inside, I have to go ahead and do the chain rule again. I have everything raised to a 1/2 power, so that's going to be 1/2 times x squared plus 1 to the negative 1/2, okay? And this is just simply the same thing when you take the derivative of x squared. It's the polynomial rule. You take the exponent, you put it out in front, then you have x, and then you have exponent minus 1. So here's 1/2 coming out, middle part stays the same, exponent minus 1, okay, but it's still not done because you have to do the chain rule again because the inside here was not x. The inside was more complicated than that. So you multiply by the derivative of the inside. The derivative of the inside here is 2x. Okay, this is a perfect example of the chain rule being used out the wazoo. You had a function within a function within a function, really, because you had the hyperbolic cotangent inverse, and then inside of that you had a complicated radical with an x squared in there. So we took the derivative of the cotangent inverse first and plugged in the argument that we had here, and then we had to take the derivative of this. But this was like x squared plus 1 raised to the power of 1/2, so the 1/2 came down, then we had the inside, 1/2 minus 1 is negative 1/2, and then we weren't done because this was still not in simplest form. We needed to take the derivative of the inside. Derivative of 2x of x squared is 2x. Okay, so now you just have to do some simplification. df dx, okay, is just simply going to be equal to this. Let's go ahead and do some simplification. This 2 is going to cancel with this 2, so that kind of disappears. This x is going to be on top of the fraction, so you're going to have x, okay, over. Now on the bottom, I still have my 1 minus, and look at what I have here. I have x squared plus 1 square root, and then I have it squared. The square root and the square cancels, so what I'm going to have is x squared plus 1. The square and the square root cancel. And notice I kept everything the same. I haven't done anything with this negative sign. I've just said 1 minus, and I keep the inside. I want to make sure I do not get confused. Now over here, x squared plus 1 to the negative 1/2, he's going to go down on the bottom because it's a negative exponent. So I choose to simplify it that way. X squared plus 1 to the 1/2. Notice he becomes a positive 1/2 because I dropped him down to the denominator. So what I'm left with is the x on the top, this guy here with the radical stripped off because I squared him, and then this term dropping down to the bottom as well because he's a negative exponent there. So the next thing I'm going to do is continue simplifying. df dx is equal to x on the top, that stays the same. And now what I'm going to do is I'm going to work on what I have here. I'm going to simplify this, okay? You see, I have a negative 1 here, and once I distribute this negative 1 in here and distribute it over here, I'm going to have a 1, and I'm going to have a minus 1. Those are going to cancel. This negative x squared is going to hang around, so I'm going to have negative x squared. That's all it's going to remain out of this term here, there. And then I'm going to have it multiplied by x squared plus 1 to the 1/2. X squared plus 1 to the 1/2. So then to continue on, I'll have df dx. You can see right away I have an x on the top and an x squared on the bottom, so one of these exponents goes away, so it's going to be negative 1 on the top times x times the square root of x squared plus 1. That is going to be the final answer. Negative 1 over x times x squared plus 1 with a radical on top of that. So you start here, you do your derivative with the chain rule just like we talked about before, and then your 2 cancels with your 2, so that drops out. Your square cancels with your square root, so this inside part kind of comes and sticks around here, and you've got it all wrapped up with a minus sign. This term here, because it's a negative exponent, drops to the denominator, and then after that you simplify this. 1 cancels with negative 1 once you distribute this in, so he disappears. Negative x squared stays along for the ride. You have x on the top, you have this on the bottom, and then from there it's just a simple cancellation of some of your components of x, some of your exponentials, some of your exponents there in x. Okay, now what we're going to do is switch gears and do a couple of integrals here just to get some practice. So what if you have the integral of 1 over the square root of 4 plus x squared dx? And you had to simplify that. Well, the first thing you want to do, just out of matter of course here, is you want to look at, since I've given you these integrals, I mean these derivatives here, you want to look in this table and see if anything jumps out at you. Derivative of inverse hyperbolic sine here is equal to this, so we know the integral of this quantity is equal to inverse hyperbolic sine, but it doesn't quite match. You see, this doesn't look exactly like that. So the trick is going to be to see if we can make it somehow look the right way. We want to see if we can make it somehow look the right way. Okay, so the first thing we want to do is we want to see if we can get this 4 out. We want to see if we can get that 4 out. So the way you do this is you have to do it real methodically. You know you want to take him out, but he's all wrapped up in a square root sign, so you have to be real careful about how you do it. This is how you would do it step by step. You have a square root on the bottom. You want to pull a 4 out, and so you have 1 plus x squared divided by 4. This is all going to be underneath a radical. Now you see, this is exactly true what I've done, because if I take 4 and multiply it in, I'm going to get back exactly what I had. So that's step number 1, dx. Because the square root of 4 is 2, and so that comes out as a 2 on the bottom, and I can pull that out as a 1/2 outside of the integral, okay, times 1 over the square root of 1 plus, and I'm going to write this as x over 2 squared dx. And you'll see why I do that in a minute, but you see I've changed nothing. I've taken the square root of 4, so he becomes a 2 outside here on the denominator, so I can pull him out as a 1/2 because basically I have an implied 1 on the top of the 2 there, so they come out as 1/2. Notice that if I multiply him back here on the bottom, I get exactly what I expect. I have 1/2 here, and I can move him back inside of the radical if I want to, so I've done the right thing. And then on the bottom I have the square root of 1 plus, and I'm going to write x squared over 4 as x over 2 squared, because you square the top, you square the bottom, I get exactly what I've done here. The reason I'm going to do that, never forget what you're trying to do. You're trying to get this integral to look like this integral, so that you can take his, use the fact that you know what the integral of that thing is. So in order to get that much closer, I'm going to say u is equal to x over 2. I'm doing that because when I rewrite my integral, I'm going to have u squared in here, and that's going to look very similar. In fact, it's going to look exactly like that. That's exactly why I'm doing it. So then du is equal to 1/2. Du dx is equal to 1/2. Derivative of u with respect to x is 1/2 because 1/2 is a constant sitting out there in front of the x. Okay? And then dx is going to equal 2 times du. Move the dx over here, multiply by 2. Dx is equal to 2 du. Now you'll see the reason why we did that, because we do 1/2 times the integral 1 over square root 1 plus u squared times, we substituted in our value of u, but now we have to multiply by our definition of dx, which is 2 times du. Okay? And when we do that, you see right away you get a nice cancellation. 2 cancels with 2 on the bottom, and now you have an integral exactly in this form. 1 over square root of 1 plus u squared is exactly that. So what the answer is actually going to equal, you know that the integral of this is equal to the inverse hyperbolic of u plus a constant, because your integral was in terms of u, and then to finish it off you just say inverse hyperbolic of, and you plug in what u was that you had here, which is x over 2 plus a constant. So the derivative of that function is inverse hyperbolic sine of x over 2 plus a constant. So the only trick in this problem really was to go back and look at this, and if you were just given this on a test, you wouldn't really know exactly where to start, because you would be trying to think of some quick substitution or something really quick and dirty, and unless you covered the section of the class and knew that this form of an integral was very similar to this form, you probably wouldn't get very far. So here becomes a challenge of beating this thing into shape. We factored out the 4, we took his square root, we pulled him out of the integral, we rewrote this as x over 2 because I wanted to do this substitution here. I wanted to have a u squared, which is what I ended up getting once we found our differential and plugged it in. We were able to use that derivative, that definition of that integral. Okay, so that was just a quick example to show you the basic idea. I mean, you can do infinite number of integrals. You can have infinite different varieties of integrals. They're all going to be different. But basically what you need to do when you have your inverse trig functions and your inverse hyperbolic functions, and you know what those derivatives are, is now you have a whole other set of functions that if you're given an integral that looks anything like one of these on a test, you know, or you should know, that you're going to need to try to beat your function into shape no matter what you need to do, legally do it, to get it into that shape and into that form. And once you do that, you can use the fact that you know several of these integrals already to solve your problem.